So in yesterday's lecture, we have seen what are the different components of any roadway. So the features, what are the different cross-section elements what are the different elements that are present in the roadway, and what are the technical terms that is being used for these are being discussed. So in this lecture, we will be seeing and we'll be understanding the most important concept in highway geometric design, that is side distance. So this topic is really important if you are looking for any gate, if you are looking for gate exam or PUC exams. So for a safe and efficient operation of vehicle will be depending on what all. So suppose you're driving your vehicle, can be a two-wheeler, four-wheeler, okay, or a cycle. So what is the key feature, or what is that influences safe and efficient operation of a vehicle? So it mainly depends on the obstruction that is present on the road. Okay. So in this context, when the term obstruction comes into picture, you have the side distance coming. So side distance will be defined from any point. From any point, what is side distance? That is actually the actual distance along the road surface over which what a driver from any specified height, because the height of different vehicle is different, right? The two-wheeler, maybe in four-wheelers itself, how the height of sedan, and again in sedan, the different models, right? So the height of the driver, and it again attributes the physical attributes of the driver. So considering the physical attributes of the vehicle and physical attributes of the driver, the height of the driver varies from the carriageway, right? So how much distance is actually available, or how much distance available, or the actual distance that is available or along the road surface for the driver, and can have a visibility of any stationary or moving objects. So if you look at these three pictures over here, or these three images over here, you can see a driver or a car is traversing through through a horizontal curve. So here, if the driver has to see the car that is coming from here, then this line of sight should be clear, right? So this will be the path of driver's eye, or the driver's line of sight. So if there is any obstruction over here, what will happen? The driver will not be able to see the car that is coming from the opposite direction, right? So similarly here, so here you can see for this car that is located at this intersection, this driver can see both the cars that's coming from the either side, right? So we will see in detail what are the few cases where you have. So side distance, mainly you have stopping side distance, intermediate side distance, overtaking side distance, headlight side distance, and safe side distance. So stopping side distance is nothing but you find a vehicle that is coming from the opposite line, from the opposite direction, and what you should be doing, you should be stopping the vehicle in case if it is about to collide, right? So in order to avoid collision, or in order to avoid collision with any object, you have to stop the vehicle. So there should be some distance that is available so that the driver can stop, right? First you have to think whether you have to stop, so that reaction times comes into picture. Then you start applying the brake. So again, during the braking, sudden braking will not happen. The vehicle will be moving for some distance. So taking the no factor for the time that is required for the driver to perceive the situation, and the time and the distance that is required for braking, that comes as stopping side distance. Intermediate side distances, whenever the stopping side distance is not available for a two-lane road, intermediate side distance will be provided. So intermediate side distance is nothing but it is actually twice the stopping side distance. So we will see in detail when we discuss in numerical. So it is twice the stopping side distance. So this is usually being provided when overtaking side distance is not possible to be provided. When there is some see, when a vehicle has to overtake, there should be it should be a two-lane road. right? So if there is no sufficient space to provide overtaking side distance, intermediate side distance will be provided, and intermediate side distance will be twice the stopping side distance. Then you have the overtaking side distance again. So that is the distance that is required for a vehicle to overtake. So those of you who drive understand how you overtake, right? First you increase the speed, you accelerate, and then there will be some distance before the vehicle. So if you have vehicle A and vehicle B over here, so A has to overtake B. So you have to accelerate for some distance, then you have to overtake, and then again you have to rejoin the lane. So this much distance will be required, right? So that distance is nothing but overtaking side distance. Then headlight side distance comes into picture when you have curves, when you have vertical curves. So vertical curves, again, you have valley curve and summit curve. So I'll show in the next diagram. So here, this is the side distance at any horizontal curve. So see, the vehicle is coming from this side and you have a vehicle coming from this side, right? So there is some obstruction to the vision for these two vehicles such that uh, the the driver is not able to see the vehicle coming from the opposite direction. So this safe distance or this side distance has to be computed. Now, side distance at the intersection. So that means, see, there are two vehicles coming. So they're not able to see this. This is the side distance that is available, but this is actually what the side distance or the driver's line of sight. So the driver's line of sight is having some obstruction here. Similarly, here also, this is a sight line, right? But this is a side distance that you will be computing. Then at any curve, so at any curve, if there is some obstruction, the if the vehicle is somewhere over here, the headlight will be coinciding over here. So what is that distance that is required at any curve? So now we will in detail discuss stopping side distance. So in today's lecture, we will be seeing what stopping side distance is, how stopping side distance is computed, and then we will go through 4 to 5 numericals in stopping side distance computation. So stopping side distance, see, you are driving on a plain road, you find an animal, or maybe you find some obstruction. So what is it? You detect the hazard from here. And then what happens? There will be some reaction time. So usually the reaction time prescribed by IRC for a well-fit human being is 2.5 seconds. So we will see how reaction time will be varying with respect to different people and different situations. So reaction time prescribed by IRC is 2.5 seconds. So here, this car has detected a hazard or detected an obstruction. So it has to apply the brake. So the reaction time is 2.5 seconds. So this distance, that is, see, the vehicle or the driver has detected the hazard from this point. So after some seconds, maybe 2 seconds, so 2.5 seconds, the driver decides to apply the brake. So this distance that has been traveled is known as the reaction distance or the lag distance. This term is important. This lag distance. And after this reaction distance, the driver decides what is to be done. So he or she applies the brake. So the distance that is being traversed by the vehicle from the moment of brake applied and the vehicle stops, that is nothing but the braking distance. So the stopping side distance is nothing but the lag distance and then the braking distance. Okay. So stopping side distance is the minimum side distance that will be available on any carriageway at any spot having sufficient length such that the driver is able to stop the car. And there is again one more condition. This minimum side distance is such that the driver is traveling in the designed speed. Okay. And he should be or he or she should be able to stop the vehicle safely without any collision with the obstruction. Is this concept clear? So this will be the minimum distance that should be available on any highway, provided the driver is moving on a in the design speed and the driver is able to stop the vehicle or stop the vehicle without any collision to the obstruction. Okay, the driver should be able to stop the vehicle safely without any collision. So this will be depending on what all factors. What all factors will this depend on? So you are driving, you find an obstruction, and then you have to stop. So what all parameters does this depend on? How much distance will it actually take? First will be obviously what the speed, right? The design speed of that road. Okay, so though the design speed is 60, if you're traveling at 80 or 90, the stopping side distance that you require will be different. But the highway or the pavement will be designed for that typical side distance. So you should know the design speed or the speed of the vehicle. Then was the reaction time, or how much time did the driver take to realize that okay, there is an obstruction and he or she has to do something. Then the payment characteristics. So in payment characteristics, what contribution will come? It's mainly the friction contribution. So the computation of side distance depends on the reaction time of the driver, the speed of the vehicle, efficiency of the brake, frictional resistance between tire and the road, and then the gradient of the road. Okay. So the reaction time of the driver, you have an important theory that is nothing but PIEV theory. So the reaction time can be took into two. One is the perception time. Perception time is nothing but the time that is required for the driver to understand. Okay, it's the time required for the driver that the driver has to realize that the brakes must be applied. Okay, and that will be how will you compute that time, that reaction time? It will be the time the moment the driver sees the obstruction to the moment the driver applies the brake. So that is nothing but the perception time. Okay, so the brake reaction time is nothing but the person or the driver will be applying the brake and it has to stop. That is nothing but the brake reaction time. So usually there is no bifurcation given for reaction time of the driver. It has been combined as the total reaction time. So for reaction time, you have PIEV theory. PIEV is nothing but perception. So first what happens is there is a stimulus. Stimulus is what the obstruction that you're finding. So once you find the obstruction or once it acts as a stimulus, you perceive it, right? It goes to the brain. So there what happens? There is some intellection time. So that is the time that is required for the driver to understand the situation. Okay, and he has to compare the different thoughts and then regroup and then register this new sensation. So that is nothing but intellection time. Okay, so perception, you perceive the situation, uh, you perceive it by the eyes, like you see the obstruction, or sometimes you might hear the honking, right? So that is if you're not able to see the obstruction, you might be able to hear. So that is the perception. Then intellection time. Then emotion time. So what happens is suddenly if you find an obstruction, the immediate reaction will be fear, right? So here the emotions come into picture, and then violation time. So here what happens? The response of the driver will be there. So combining this perception, intellection, emotion, violation time, that is nothing but the reaction time. So during this violation time, the driver thinks that okay, he has to stop or maybe he has to overtake. So usually if there is an obstruction in the middle of the road, the only possibility is stopping the vehicle. Okay, so that theory explains the reaction time of the driver. Okay, so here this has been illustrated here. So this diagram is important. You have a stimulus, you perceive the external obstruction, intellectual action happen in the brain, the time that is elapsed for emotional sensations and other mental disturbances happen. So there might be many mental emotions. You might be afraid, there might be anger because you see that someone is driving in that way, or sometimes you might be having some superstitious thoughts. So all these emotions play, and then the volition time is nothing but the driver decides to apply the brake, and then the response come as in applying the brake. So now how will this, or how will a reaction time get low? So this is the a typical data that is being collected by Transport Research Laboratory. So here it's been shown that 13% of the time, or 13% of the distracted driver, usually what we have seen in IRCs, they give 2.5 seconds, but usually an undistracted driver, that is there is no distraction and the driver is concentrated only on driving, then the driver will be taking only mostly like 1 second. But if there is some distraction, right, 13% of the time the distraction is due to drink drive limit, 21% when he's on drugs, 27% when the hands are free with phone, but still, they might be talking. It's hands-free phone. That means the phone might be connected to Bluetooth, or they have a stand for the phone, but still there might be some thoughts that might be happening during the conversation. 37% happens when they're texting, and 46% of increase in distracted time when the phone is being held in hand. So from 1 second, 13% increase means 1 into 13 by 100 plus 1. So that means almost 1.13 seconds. So here they take almost 1.46 seconds here. So next, the next factor that that defines the stopping side distance is the speed of the vehicle. So first, what happens is how much the distance the vehicle moves during the total reaction time. That actually depends on what what was the speed of the vehicle, right? Then the second distance, that is the braking distance, or the distance moved by the vehicle after applying the brakes, also come into picture. That also is evident on the initial speed of the vehicle. So what will happen? So if the speed of the vehicle is higher, then obviously the stopping distance that is required for the vehicle to completely stop will also be higher. So next is the frictional resistance between the tire and road. So when you have that we have already seen about the skid resistance or coefficient of friction in pavement characteristics, right? So as the frictional coefficient decreases, what will happen? The braking distance will be increasing, right? So here when the road is wet, what happens? The frictional coefficient will be less. So the stopping distance that will be required will be more. Okay. So this picture shows, so stopping side distance is 1.5 times longer on wet road and 3 times longer on iced road. So iced road scenario is not actually found in India, but this you can visualize. So usually during rainy season, the stopping side distance, that, see, you might think that okay, within this distance you will be able to stop the vehicle, but for wet road, since the friction coefficient or the skid resistance is less, the distance that you might require to stop the vehicle will be more. It's usually 1.5 times more than that required on a dry road. And next is the efficiency of brake, right? If the brake efficiency is said to be 100%, when do you say that the brake efficiency is 100%? You apply the brake and the wheels are completely locked, right? Wheels are 100% locked. So then you call the brake efficiency to be 100. Okay, so now we will see the computation of stopping side distance. So this is important concept. So from this diagram, we have seen stopping side distance is nothing but the reaction distance or the lag distance plus the braking distance. Now we will divide these two into lag distance and braking distance, and we will compute lag distance separately, braking distance separately, and then we will see how to compute stopping side distance in overall. Yeah. So lag distance we have seen, it is, what is that lag distance? It's the distance the vehicle would have traveled during the reaction time. And what will be that distance? That will be given by V into T. There's nothing but a simple equation to determine distance. What is distance? Velocity into time. So if the design speed is given in kilometer per hour, so you have to convert that in meter per second. Either you can directly opt kilometer per hour, but in that case you have to convert time into what? Time into hour, right? So usually, since the reaction time is given in seconds, it's always better the design speed be converted to meter per second. But design speed will usually will be given in kmph, right? In your vehicle also, you might have seen the the speedometer is set in what? kmph, right? So speed will be given in kmph. It is important you convert the speed into meter per second. Why should you convert it? Because the time that will be given will be seconds. So you cannot multiply kilometer per hour and seconds. Okay. So the lag distance is capital D is nothing but in kilometer per second into T. So kilometer is 1000 per hour. So hour, how will you convert to seconds? 60 minutes and 60 seconds. So that will give you 0.278 VT. approximated to 0.28 into velocity in kilometer per hour into t. So this much meters is the lag distance. So as per IRC recommendation, as I've told, the total reaction time of the driver is taken as 2.5 seconds. So now the stopping side distance. So next is the braking distance. So braking distance is what? The distance that's traveled by the vehicle once the driver has applied the brake. Okay. So for a level road, what happens is the work done in stopping the vehicle and the kinetic energy of the vehicle is being equated for a level road. Okay, so when you have inclination or when you have gradient, that is a different scenario. We will see in the next slide. So when it is a level road, the work done in stopping the vehicle is being equated to kinetic energy of the vehicle. So what will be the work done? The work done is nothing but what is the work done? So if the vehicle is moving, so the work is done against the friction to stop the vehicle. Okay. So that is nothing but if F is the maximum frictional force that is developed, capital F into L. You know work done, right? What is work done? Force into distance. So capital F into L. Now this capital F is nothing but F frictional coefficient into W. So if you remember the concept of friction from your elements of civil engineering, so this is the weight. Yeah, this is the weight. Okay. So the vehicle is moving in this direction. Frictional force will be developed in which direction? In this opposite direction. Right. So this is nothing but what? F into W. Right. So here F into W into L. So where W is the total weight of the vehicle. Now kinetic energy, how will you compute kinetic energy? It is half into mv square. So for the design speed, we assume that the vehicle is moving in the design speed. So half into m into v square. M is nothing but weight by g, right? You know the relationship between weight and mass, right? V squared by g. So equating the work done against friction and kinetic energy, you get FWL equals half into WV squared by 2G. Okay. So cancelling W and W on both the sides and taking F this side, braking distance L is nothing but half into V squared by 2GF. So total SSD or the stopping side distance is nothing but the lag distance and the braking distance. Lag distance we have computed in the previous slide. It is V into T plus 1 by 2 into V squared by 2GF. Okay. So the table that has been shown over here is the longitudinal frictional coefficient that you have to take for the speed. So this is from IRC. Okay. So I will share the IRC code in the classroom. I'll share IRC in GCR so you can go through the IRC and understand where this table is coming. So the speed, for the design speed, this is the longitudinal frictional coefficient. So now when you have an inclined road, okay, or there is a gradient. So I'm considering an upward gradient of theta. Okay, so let us assume that the vehicle is moving downward. So you have the frictional force that is developed in this direction. So the inclination, let us take the inclination of the pavement as theta. See this diagram will not be shown in your textbook. Okay. So let us take the inclination as theta. So you know how to solve the force, right? Weight. Then you have the the components of weight along both the directions. You have mg cos theta. So if this is theta, this will be 90 minus theta. You have theta here again. So if this is mg cos theta, mg sin theta. Right? So the component of gravity which is acting parallel to the surface, what will be that? Mg sin theta, right? So that since the inclination is less, very less, so you can approximate sin theta to tan theta, and tan theta will be nothing but what? It is the slope. So mg I take as W, tan theta is nothing but n by 100. Is this clear? Yeah, so is this clear? So mg sin theta is the component that is parallel, and yeah, so mg sin theta is a component that is parallel to frictional force and that is parallel to the surface, which will be adding to the braking force. Okay, So now if we take, so this is the component of gravity that will be coming along with the braking force. So you have Fw plus Wn by 100 into L. So Fw, we have seen how we got Fw. So this is Fw into L. Okay. So here we have Fw into L plus Wn by 100, which is equivalent to what? Which is equivalent to the kinetic energy. That is nothing but half into Wv squared by G. So again, you substitute, you get what? V squared by 2G into F plus N by 100. So this is for upward gradient. So if you're having downward gradient, it will be minus. Okay, so the sine theta component will be acting in the opposite direction. Okay, so SSD for the gradient road you can take as Vt plus V squared by 2G into F plus or minus 0.01 N, which is given in percentage. Okay, is that clear? Okay, now if you're taking SSD for a two-way traffic on a two-lane road, so the diagram will be looking something like this. You have a two-lane road. That means you have vehicular traffic in. Okay, so in this case, SSD is nothing but whatever SSD you compute. Now, when you have a single lane road and then you have a two-way traffic, so in this case, SSD will be twice the SSD that is computed for a single lane road. Okay, so whatever SSD you compute, that into 2 will be SSD for two-way traffic on the single lane road. Is that clear? Yeah. So this is the stopping side distance, the safe stopping side distance for various speeds. Okay, so for different speed, the reaction time is given. The coefficient of friction is also been given as per IRC. You compute it and then you calculate. So this is the design safe stopping side distance that is being given. So this you can refer IRC 073 geometric design standards for rural highways. Okay. So this shows the speed and the safe stopping side distance. So now we will quickly go through one numerical. I want all of you to have one book with you. So note down the question. Calculate the SSD for V equals 50 kmph for a two-way traffic in a two-lane road and two-way traffic in single-lane road. Okay, so here the data that is given is, what are the data given? V equals 50 kmph. So now I have told you this velocity, since it's given in kilometer per hour, you have to convert into meter per second. So you convert, how will you convert into meter per second? Capital V into 1000 divided by 60 into 60. So you get V as 13.9 meter per second. Okay. So now SSD for V 50 kmph. So T is as per IRC, you can take reaction time as 2.5 seconds. Now, if frictional force is not given and if code is given, then you can refer the code and let's see. Yeah. So what was the speed that was given? The speed was, what was the speed given?
50, ma'am.
Yeah, 50. So when looking at the table, when design speed is 50, what should be the frictional coefficient that you have to opt? What should be the frictional coefficient that you have to opt?
Point
Point?
0.37.
Yeah, 0.37. Good. Okay, so you take F equals 0.37. Now you know how to compute SSD, right? Since there's no mentioning about the gradient, we take the equation for a plain road. So it is Vt plus 1 by 2 V squared by 2Gf. So V is nothing but 13.9 into 2.5 plus 13.9 square divided by 2 into 9.81 into 0.37. So you substitute, just substitute and get the value. Anyways, I've computed and given the value there, but let me know whether you're getting the same value there.
Yes, ma'am.
Okay, you're getting 61.4. Now, only for this numerical, I'll be solving the numerical in kilometer per hour conversion also. So if you're considering it is as kilometer per hour, so we will be directly taking it as 0.278. How will you get here 0.278? How will you get here as 0.278b? Anyone? So if you're taking velocity as kmph, what will be the 0.278? Okay, so this is again the 1000 by 16 to 60. So we take 1000 in by 16 to 60. The same conversion you do here, you get 254. That is again multiplying by 2 and 9.81. So if you substitute by capital V also, you should be getting the same answer. Okay. So now we have two clauses here. Two-way traffic in a two-lane road. So for two-way traffic in two-lane road, what will be the SSD value? That will be, what will be the value for SSD? Yes, am I audible? Disha, can you hear me? Yeah,
Yes,
so
ma'am.
what is the value of SSD that you have computed? What's the value of SSD that you have obtained?
61.4.
Yeah, 61.4. Good, Sneha. So for a two-way traffic road on a two-lanes road, SSD is again the SSD that we have computed. But what about SSD for two-way traffic on a single lane? That will be twice. Very good. So that is
122.8.
122.8. How will you get 122.8? That is twice 61.4. So is this numerical clear? Is anyone having any doubt in this numerical? Because the easiest and the simple numerical that is there. Further from this understanding, you have to solve the next numerical. So is this clear? Anyone having any doubt? Is there anyone having any doubt? Okay,
No,
so
ma'am.
I hope it's clear. So now we will note down the next problem. Please note down the next problem. Find the minimum side distance to avoid head-on collision of two cars approaching at 90 kmph and 60 kmph. Given t equal to 0.5 second, f equals 0.7 and brake efficiency of 50% in either case. Alekya?
Yes, ma'am.
Yeah, did you compute the previous numerical? Did you get the SSD value?
Yes, ma'am.
Okay, so here you have to determine the minimum side distance to avoid head-on collision. So there are two cars that are approaching and the speed of each car is also given. So this is the situation. Okay, you have one car approaching from here and another car approaching from this side. So how will you compute the minimum side distance that is required so that the vehicle doesn't collide? How will you compute SSD here? Anyone? How will you compute SSD in this condition or in this scenario? Monica,
Yes, ma'am.
yeah, how will you compute SSD here? Rishabh, yeah, Rishabh, how will you compute SSD in this situation? See, you assume that you are
Uh,
driving one of the vehicle. So to avoid the collision, how will you compute the SSD? So both the vehicle has to stop, right? Let's assume that both, and it's not an assumption, both the vehicles are no, are moving. So both the vehicles has to stop, and both the vehicles are having different speed. So assume that you are in one of the vehicle. How will that SSD be computed? Yes, Rishabh. Some thoughts into this.
don't know.
Sorry.
Ma'am, what is it? Like lay distance plus braking distance. If we add them both,
No, yeah, lag distance and braking distance. What will you do?
we'll add them both.
But how will you compute lag distance and brake distance? So you're computing single lag distance and braking distance?
Yes, ma'am.
No, then I should say that you're still not safe to drive in the on the road. Anyone? Nine? Yeah. How will you compute the minimum side distance to avoid head-on collision? Srishti?
Ma'am.
Yeah. How will you compute the minimum side distance that is required such that there is no collision?